Welcome to your lecture in Principles of Computer Networks. In this lecture and the coming lecture, we will discuss the medium access control sublier. In this lecture, we will cover the channel allocation problem and multiple access protocols. Generally, there are two types of networks, point-to-point networks and broadcast networks. Broadcast networks, also known as multicast channels or random access channels. The main issue with random access channels is who gets to use the channel when there is competition for it. Consider a conference call where everyone is trying to talk and no one is listening. The data will be scrambled. The protocols used to determine who goes first in multicast channels belong to a sublier of data link layer called medium access control sublier. The MAC sublier is the bottom part of the data link layer, where the upper part is logical link control. How to allocate a single channel amongst competing users? This can be done statically using time division multiplexing or frequency division multiplexing, for example. And it can be done dynamically using one of the protocols we're going to study in this lecture, Aloha, SYSMA, collision-free protocols, limited contention protocols. Statically, like using frequency division multiplexing, if there is a small number of users and a heavy traffic, the FDM will work just fine. But if there is a very large number of users and varying traffic or burst traffic, that's to say traffic that is low at times and very high at other times, FDM won't work. Same applies for time division multiplexing and any other static allocation method. Our solution here is to assign the channel dynamically. And to do this, we have some assumptions to make first. We have 5 key assumptions. First, independent traffic. That's to say, each station creates independently its own traffic. Single channel. There is a single channel shared by all stations. Collision assumption, which means collision is happening or going to happen. Time assumption. Time can be continuous time or slotted time, and these are mutually exclusive. Carriers assumption, there will be carrier sense or no carrier sense, and these also are mutually exclusive. The protocols we're going to study in this lecture are Aloha, carrier sense multiple access protocol, collision-free protocols, limited contention protocols, and wireless LAN protocol. Aloha is the first protocol we will study. It's a very simple protocol. We just let the user transmit whenever they have data to send. There will be collisions. Whenever there is a collision, the user will wait for a random amount of time and then will resend the data. There are 2 types of Aloha, pure Aloha and slotted Aloha. Both were basically designed to link remote stations to a central computer in Hawaii. And that's where Aloha comes from. Aloha is hello in Hawaiian. In pure Aloha, frames are transmitted at completely arbitrary times. Any user has data to send, will send it. Collision happens, data will be resent within a random time. A frame will not suffer a collision if no other frames were sent from the time it was fully sent until it was fully received. Let T be the time required for the one frame to be sent. If any user has generated a frame between T0 and T0 plus T, there will be a collision. The frame will collide with the beginning of the first one. Similarly, if any other frame started between T0 plus T and T0 plus 2T, it will bump into the end of the frame. As you can see here, for the shaded frame, it will collide if a frame was sent between T0 and T0 plus T, and or from T0 plus T to T0 plus 2T. So the period from T0 to T0 plus 2T is called the vulnerable period for the frame. Aloha was first proposed in 1970. In 1972, Ropost published a method for doubling the capacity of Aloha systems. He proposed that to divide time into discrete intervals called slots, each interval corresponding to one frame, that's to say T. This approach requires users to agree on slot boundaries, and to achieve this, a special station will emit a beep at the start of each interval like a clock. No station is permitted to send whenever the frame is ready. It's required to wait until the beginning of the next slot. This way, the vulnerable period is halved for slotted Aloha. But for a slotted Aloha also, any small increase in the channel load will drastically reduce the performance. As you can see here, a comparison between slotted Aloha and pure Aloha. You can see that slotted Aloha has increased the performance into almost double. There are some protocols that are perfectly valid, but has fallen into disuse for political reasons, for technical reasons, for some company wants its protocols to be used and enforcing the technology it uses, for various reasons. After some time, someone will come along and discover this protocol will solve a certain problem we're looking for a solution for, and dig it from the dirt and start reusing it again. This is why in this lecture, or rather in this chapter, we're going to discuss both. Protocols are currently in use and some elegant protocols that are not widely used now, but can be in use again soon in the future. The first protocol we're going to discuss, or the first few protocols we're going to discuss, fall under a category that called CISMA, Carrier Sense Multiple Access Protocols. The idea is very simple. If no one listens and we all start talking at the same time, this will make a huge chaos and lead to poor channel utilization. If we listen first, then we speak, there will be better channel utilization and much less collisions. There are two types of CISMA. CISMA SD with collision detection and CISMA without SD without collision detection. Without collision detection, there are three protocols we're going to study: persistent CISMA, non-persistent CISMA, and P-persistent CISMA. Persistent CISMA is very simple. Before sending any station, we'll sense the channel. If the channel is idle, the station transmits a frame. If the channel is busy, the station will wait until it becomes idle. Then the station will transmit a frame. If collision occurs, the station waits for a random time, then starts again. The protocol is called persistent because the station is continuously examining the link until it's free. As simple as it is, it seems that it's perfectly fine to use CISMA without collision detection, but as we can see here, in the case of two stations were ready during a third station was sending, they will both wait patiently until the station finishes sending and the channel is idle. Then they will immediately start sending their data to collide. If they have waited patiently, a little bit patiently, that the collision wouldn't happen. For this protocol, the bandwidth delay product has a very important effect on the performance. There is a small chance that after a station begins sending, another station will become ready and send at the same time. That will happen if the signal from the first station did not reach the second station. The second station will sense the the carrier and will find it idle and start transmitting, causing a collision. But yet, it's better than Aloha. The non-persistent SIGMA is different from persistent SIGMA in one manner, that it's not persistently checking the link until it's idle. It will actually simply check the link. If the carrier is idle, it will send. If the carrier is not idle, it will wait for a random amount of time to check it, then check it again. It has better channel utilization than one persistent SIGMA, but it has longer delays than one persistent SIGMA. The third protocol, the P-persistent SIGMA, when transmitting station has a frame to send, it sends the channel. If the channel is busy, it waits until the end of transmission, then transmits with probability of P. Hence, the name P-persistent SIGMA. When the frame is ready, the transmitting station checks whether the channel is busy or idle. If the channel is idle, it transmits the frame immediately. If the channel is busy, the station waits, continuously checking until the channel becomes idle. When the channel becomes idle, the station transmits the frame with probability of P. With probability of 1 minus P, the channel will wait for the next time slot. If the next time slot is idle, it again transmits with probability of P1 minus P. The station repeats this process until either the frame was transmitted or another station begins transmitting its data. If another station begins transmitting its data, the station will wait for a random amount of time and restart the algorithm. As we have noticed, this is applied for slotted channels, and it has better utilization than one persistent SIGMA, and the refinement of P-persistent SIGMA was developed for Wi-Fi. Here we can see a comparison between different protocols. The lowest performance goes for pure Aloha. Next comes slotted Aloha, then 1 persistent SIGMA, then 0.5 persistent SIGMA, then 0.1 persistent SIGMA, then non-persistent SIGMA, then 1.01 persistent SIGMA. Next protocol to study is SIGMA with SD, Carrier Sense Multiple Access Protocol with collision detection, which is an enhancement over SIGMA. Without collision detection, as soon as the stations detect collision, they stop their transmission for a random time and then they will restart again. With collision detection, there are one of 3 possibilities. It's contention, that's collision detection, transmission, or idle when there is no data to be sent. So the channel utilization is much better. For how long it will take a station to realize that there has been a collision? A time to transmit a frame, for example, that won't be enough because the frame might collide at the very end of the link, data of the link, of the physical link. So the time for transmission from one end to the another end of the cable, that sounds better. Actually, the worst case, if the station cannot be sure if it has seized the channel until it has transmitted for 2T, 2 tau, where tau is the time for a signal to propagate between the furthest 2 stations. That's to say, the time, the round trip for the signal to reach at the far end of the cable and comes back. Our 5th protocol for today is the basic bitmap method. It's very simple where there is a bitmap. If the station wants to send the frame, it will set its bit to 1. If not, the bit will remain 0. Each contention period consists of exactly n slots, number of stations. If station 0 has a frame to send, it will transmit 1 bit during the slot 0. No other station is allowed to transmit during slot 0. Regardless of what station 0 does, station 1 will get the opportunity to transmit a bit during slot 1, but only if it has frame to queued, has frame to send. In general, slot J is reserved for station J to announce that it has a frame to send. Else, the bit will still be 0. After all the n slots have passed by, each station had the knowledge of which stations wish to transmit, and they will start transmitting in a numerical order. Since everyone agrees on who goes next, there are no collisions. As you can see here, station 1, station 3, and station 7 declared their intention to send data. So frame 1 is sent first, frame 3 is sent next, frame 7 is sent after. In the second contention period, station 1 and station 5 declared their desire to transmit data, so frame 1 then frame 5 were sent. In the third contention period, only station 2 wants to send data, so frame 2 was sent. You can see there is no way for a collision to happen. The other protocol that prevents collision is token passing. A token represents a permission to send. If the station has queued frame, when it receives the token, it can send the frame. Otherwise, it will wait until the token reaches it. When it finishes sending the frame, it will pass the token to the next station. If the station has no queued frame, it will simply pass the token. There are two types of token passing technologies, a token ring and token bus. For the token ring protocol, the stations are connected on one next to another in a single ring. The token is passed from one station to another. If the station has a frame to send, it will hold the token until the frame is sent. Then it will release the token to the next station. This happens in a single direction. That's how collisions never happen. The problem with both basic bitmap and token passing is that the overhead is 1 bit per station. That does not scale well for networks with thousands of stations, and the delay will be huge. This is why binary countdown protocol, because we can do better by using binary station addresses with a channel that combine them. A station wants to use the channel will broadcast its address in a binary bit string, starting with the highest order bit first. The bits of each stage address position from different stations are Boolean all together by the channel. To avoid conflicts, as soon as a station sees that a highest order position that is 0 is replaced by 1, it gives up. The binary countdown protocol implicitly assumes that transmission delays are negligible. For example, if you have station 0010, 0100, 1001, and 1010 are trying to get the channel, the first bit of each one of them, the highest order is 0, 0, 1, and 1 respectively. They are ORed to form a 1. So it's stations 0010 and 0100 sees the 1 and knows that there are higher numbered stations competing for the channel, so they give up. 1001 and 1010 continue. The next round, it's 0 bits, so both stations continue. The next round, it's a 1, so 1001 gives up. The winner is 1010 because it had the highest address, as we can see here. As we have seen with contention methods like Aloha, Slotted Aloha, Pure Aloha, SYSMA, they work well under low load, and they're preferable because they have low delay. Under high load, the contention methods become increasingly less efficient. Without contention methods work well under high load, but under low load they have very huge delay. So why not to try to combine both in limited contention protocols that have the pros of each? We need a way to assign stations slots dynamically, with many stations per slot when the load is low, and few stations per slot when the load is high. An example for this is adaptive tree walk protocol. In adaptive tree walk protocol, the stations are partitioned into groups in a hierarchical manner, as we have seen. The contention period is divided into discrete time slots. For each slot, contention rights of the station are limited. Under high loads, all the stations, under light loads, all the stations can participate, just like Slotted Aloha. However, under heavy loads, only a small group of stations are allowed to give in a slot. All the previous protocols were good enough for wired LANs. But what about wireless LANs? Let us assume that we are using SYSMA for a wireless LAN, where you just listen to other transmissions, only transmit if no one else is doing so. The problem here is, what if two stations were transmitting to the same station? Their frames will definitely collide at the receiver. So it's more important to see if the receiver is free before sending, rather to see if the channel was free before sending. To see the nature of the problem, let us assume that we have 4 nodes, A, B, C, and D. In total disregard if they are access point or laptops. The radio range is from A to B, from B to C, from C to D. So A is likely to interfere with B, while C is likely to interfere with B and D, not A. What if A is trying to send to B, while C is trying to send to B? A and C will collide at B. This is known as the hidden station problem. The problem of the hidden station is not being able to detect a potential competition for the medium because of the competitor is too far away. What if C is trying to send to D while B is trying to send to A? C will falsely sense that the medium is not free because it will sense the signals B is transmitting and will not send to D without knowing that D is free. So what shall we do? As we say, the problem is the station really wants to know whether or not there is activity around the receiver, not the sender. The solution is multi-access with collision avoidance protocol. In this protocol, the sender sends request to send to the receiver, and the receiver will reply with clear to send to the sender before exchanging any data at all. Your reading assignment for today is Computer Networks Top-Down Approach, 7th edition, Chapter 6. No writing assignment for this week. Thank you very much. See you next week, inshallah.